The paper we are diving into today is called StereoWorld, Geometry-Aware Monocular-to-Stereo Video Generation. And it's really tackling one of the biggest bottlenecks in immersive tech right now.
It really is. I mean, you've got this huge demand for immersive content, especially with devices like the Apple Vision Pro and MetaQuest hitting the market. But the problem is making native stereo video is hard and it's expensive.
Right.
So StereoWorld comes as the first fully end-to-end diffusion framework that can take all that existing monocular video, normal 2D video, and turn it into really high-fidelity stereo.
And that end-to-end part is so key, isn't it? Because it's moving past all those fragile multi-step pipelines we've seen before, the ones that did depth estimation, then warping, then tried to in-paint the gap.
Exactly. This is way more stable. The whole approach uses this really smart geometry-aware regularization. It's combining explicit disparity and depth supervision to make sure the 3D structure is actually, sound.
And it's not just the model, it's the data. They curated a massive data set, StereoWorld 11M. We're talking over 11 million frames, all specifically aligned to the natural human interpupillary distance.
That's the secret sauce, really, that 55 to 75 millimeter range. The result is it's a huge leap. It blows prior methods out of the water, not just in how good it looks, but in geometric consistency. You get stereo content that you can actually watch without getting a headache.
Okay, so let's unpack that. You mentioned the huge demand from XR, but producing quality stereo natively needs these expensive dual camera rigs that have to be perfectly calibrated. Why is scaling that up such a blocker for the industry?
It's a classic supply problem. We have decades and decades of incredible monocular content, but if you want to make it immersive, you can't just go back and reshoot everything. So for years, algorithms have tried to bridge that gap, and they've mostly fallen into two, let's say, fundamentally flawed approaches.
Okay, walk us through those flaws. What was the first one?
So the first paradigm, it treats the whole problem as something called novel view synthesis, or NVS.
Right, so like building a 3D model of the scene first.
Exactly. You try to recover the scene geometry, the camera parameters, the classic structure from motion stuff, or even modern things like NeRFs and 3D Gaussian splatting. You try to reconstruct the world digitally before rendering the new perspective.
That sounds mathematically rigorous. So where does it fall down in the real world?
Well, real-world video is just messy. You've got unconstrained dynamics, little bits of camera shake, complex motion, and NVS models are super vulnerable to any inaccuracies in the camera pose. And when those errors creep in, you get unstable geometry. That means the stereo views are jittery, they're inconsistent over time. You put on a headset and the depth just sort of swims around. It just breaks the immersion instantly.
Okay, and the other way, that depth warping in-painting pipeline, which we know from models like StereoCrafter, that's trying to avoid all that heavy 3D reconstruction, right?
Yeah. It is. It's a shortcut. It estimates depth, warps the left frame over to create a right viewpoint, and then uses a totally separate in-painting model to fill in the gaps. The bits that are revealed by the camera shift.
The disoccluded regions.
The disoccluded regions, yeah. But this introduces a really fatal architectural flaw.
And that's the decoupling, the fact that the geometry step and the texture step are completely separate.
Precisely. The in-painting part, which is deciding the color and texture of those new pixels, has no idea about the initial geometry estimation. It's just guessing. That complete break in the pipeline means you lose that critical pixel level correspondence between the two views.
And that's where you get all the infamous stereo artifacts, the weird color shifts, texture distortions, the ghosting, the stuff that gives you immediate eye strain on a headset.
It makes the content basically unusable for more than a few seconds. So StereoWorld's big insight was that you have to enforce geometric rules while you're generating the texture. And they do that with this end-to-end diffusion model that learns the geometry directly.
Okay, let's get into the engine room now. They're adapting a pre-trained monocular video model. How on earth do you get a model designed for one viewpoint to suddenly handle two, left and right, without just tearing the whole thing apart?
Yeah, and this is where I think the paper is just so clever. They're building on a really powerful base model, a diffusion transformer, or DIT, which is kind of state-of-the-art. And their conditioning strategy is, it's remarkably simple.
Simple is often the hardest thing to get right.
It really is. So instead of adding a bunch of complex new cross-attention blocks or, dedicated stereo heads, they just concatenate. They encode the left view latent, let's call it Zillow, and the right view latent Zer, and then they just stick them together along the frame dimension.
Wait, hold on. So they literally just treat the left and right views as if they were two consecutive frames in a single longer video.
That's it. That's the whole trick.
That feels like it should confuse the model's sense of time versus viewpoint.
And that's the brilliant part, because the DIT architecture already has these 3D spatio-temporal self-attention layers that are built to understand relationships across frames and space how things move over time. So those same layers just naturally start to fuse information across space, time, and viewpoint all at once. It requires zero architectural changes.
Wow, that's incredibly efficient. But even with that clever conditioning, they found that just relying on the standard RGB reconstruction loss wasn't quite enough to guarantee good stereo depth. What was missing?
The model just struggled to learn the super precise geometric shifts, the disparity, just from looking at pixel colors. With only that RGB loss, the output might look photorealistic at a glance, but the stereo perception is weak. You get flattened object boundaries, unstable depth. They needed to give it an explicit 3D signal.
Which is their geometry-aware regularization.
Exactly.
Let's dive into that, because this feels like the core contribution. It's a dual approach: disparity supervision and depth supervision. Starting with disparity, what is that lightest loss actually solving for?
So the disparity supervision, LDIS, is kind of like the close-range geometric policeman. Its job is to enforce really accurate stereo correspondence. It makes sure a pixel in the left view lands exactly where it should in the right view. This is what stops that cross-view, misalignment, and drift.
So it's the key to preventing eye strain. How do they train for that?
They don't leave it to chance. They use a pre-trained, really accurate stereo matching network, something like Stereo Any Video, to generate ground truth disparity maps. Then, during training, they have a lightweight little projector that estimates the disparity between the views the model is generating.
And I see they split that loss into two parts, log and LO1. Why both?
That's all about balancing for human perception. LO1, that's for the fine-grained pixel-wise errors. Think of it as the sharpness control. It makes sure that sharp edges, or especially text, line up perfectly. But then log, the logarithmic part, that enforces global consistency. It ensures the whole background isn't vibrating or shifting, which is a major cause of motion sickness. You really need both for a comfortable experience.
But the paper says disparity by itself isn't enough, because it only works on the parts of the image that both eyes can see.
That's its big limitation. When you shift the camera view horizontally, new content appears on the sides, those disoccluded regions we mentioned. Disparity can't say anything about those new areas because there's no corresponding pixel in the other view.
So that's where depth supervision, the LDEP, has to come in.
Exactly. If disparity is the close-up correction, depth is the global map of the whole room. It gives a complete per-pixel geometric description for the entire scene, including those non-overlapping regions. So they train the model to predict the flow for both the RGB video and its depth map at the same time.
And architecturally, they do this with dual branches. Why split the training signal up like that at the end?
It's to avoid a fight. If you force the RGB gradient, which cares about pretty colors and textures, to optimize in the same final layers as the depth gradient, which only cares about geometric structure, they can start to conflict. You get results that are kind of okay at both, but not great at either.
So they have shared initial blocks to learn a joint representation of texture and geometry.
Right.
And then it forks into two specialized branches.
That's exactly it. One branch focuses on the RGB prediction, the other on the depth prediction. This lets the model satisfy the tough geometry rules without messing up the beautiful texture generation. The final training objective is just a weighted sum of all three losses. It's a really elegant integration.
Moving from the framework to the data, let's go back to that StereoWorld 11M dataset. You said it was the secret sauce. Why is solving the IPD, the interpupillary distance problem, so important?
Oh, it's a biological constraint we just can't ignore. Almost all the prior stereo datasets like VKDI2 or Spring, they were built for machines, for robotics or self-driving cars.
Right.
So they use really wide camera baselines, sometimes more than 10 centimeters apart, because that gives a computer better depth resolution.
But that 10-centimeter baseline would look insane to a human viewer.
It's toxic. It causes what's called hyperstereoscopy. It's an exaggerated 3D effect that's physically uncomfortable. It can make you nauseous, dizzy, almost instantly. So all those huge data sets are basically useless for making consumer content.
So StereoWorld 11M was built for human comfort from day one.
Yes. They curated over 11 million frames from Blu-ray side-by-side videos across tons of different genres. And all of it is aligned to that narrow, natural human IPD of 55 to 75 millimeters. Training your model only on data that is comfortable for human eyes is what makes its output immediately usable for XR.
And this is where it gets really interesting for me, how they make this actually scale for professional use. A model that just spits out a 3-second 480p clip isn't very useful. Let's talk about their tiling strategies.
Yeah, you need to scale in both time and space. So for temporal tiling, for long videos, they split the video into overlapping chunks. And to keep it continuous, the start of the next chunk is guided by the final frames of the previous one.
So the model has context for what just happened.
Exactly. But even with that, you can get this long-range flickering effect in generated video. So they use a clever trick during training called probabilistic replacement. They sometimes swap out the first few noisy frames of a segment with the clean ground truth frames. This forces the model to learn how to stabilize really quickly.
So it makes the transitions feel more like a smooth crossfade instead of a hard cut between segments.
That's a great way to put it. And then for spatial tiling, to get from, say, 480p up to 1080p, they use blockwise latent diffusion.
Okay.
They encode the high-res input into the latent space, then they slice that latent up into overlapping tiles. They denoise each tile independently, which you can do in parallel, and then they stitch and fuse them all back together before the final decoding step. It's how you get high-res output efficiently.
Let's turn to the proof. When you look at the numbers, what do those geometric metrics to the EPE and D1 all really tell us?
They tell us the geometry is just far, far more accurate than competitors like StereoCrafter. EPE is endpoint error. It's basically the average pixel error in the disparity map. StereoWorld got the lowest EPE, which means
Less eye strain.
much less eye strain. And D1 all is the failure rate, the percentage of pixels that are just flat out wrong. Again, StereoWorld was the lowest. Hitting the best scores on these geometry metrics proves that their regularization strategy is actually working.
And when you stop looking at numbers and just look at the videos, how does that geometric accuracy show up visually?
You can see it immediately. The older models are blurry or unstable. StereoCrafter is pretty coherent, but it tends to oversmooth everything. You lose all the fine detail. StereoWorld's results are just visually faithful and rock solid over time. It keeps that crucial high-frequency detail.
The paper specifically called out text rendering as a big win. Why is text such a brutal test case for this?
Because text is completely unforgiving. It's all sharp, high-frequency edges. If your geometry is off by even a single pixel, you get immediate ghosting or blurring. It's incredibly obvious. The fact that StereoWorld renders sharp, stable text is a really strong signal that its cross-view geometry is spot on.
And of course, the human evaluators, the ultimate judges, agreed.
They did. Across the board, participants gave StereoWorld the highest subjective scores for stereo effect, visual quality, consistency between the eyes, and temporal consistency. The math translated directly into a better human experience.
And the ablation studies backed it all up. You really do need both depth and disparity supervision. Take one away, and the quality drops.
Absolutely. They're totally complementary. Disparity nails the correspondence and the magnitude of the shift, but depth is what cleans up the object boundaries and fills in the structural detail, especially in those non-overlapping regions. You need them working together.
So, to sum up, StereoWorld gives us a robust end-to-end framework with incredible visual and geometric quality, and it's optimized for real-world use with long, high-res videos. But what are the current roadblocks for an engineer who wants to use this today?
The main limitations right now are really about speed and control. First, since the disparity is learned end-to-end, you don't have a simple slider to, say, explicitly adjust the stereo baseline after it's trained. But the more practical issue is just speed.
How slow are we talking?
Right now, it takes about 6 minutes to process a single short video clip. For converting massive libraries of content on demand, that's definitely a bottleneck.
6 minutes a clip. Okay, so future work is pretty clearly focused on efficiency.
It has to be. Their next steps are all about model distillation and acceleration, finding ways to make it faster and more practical for real-world deployment.
So what does this all mean for you, the listener? We talked about that 6-minute bottleneck, but the real takeaway here is something more foundational. For the first time, a purely practical constraint, the need for human visual comfort, training to that fixed 55 to 75 millimeter IPD, has forced a generative model to incorporate biologically relevant physics. This shift, where usability and biology start to shape the models, is what's pushing us closer to truly useful, truly immersive digital content. We're literally watching generative AI being tuned by the limits of our own biology.